Mr. Tarrou. Okay, so we have now revisited the idea of sequences that we were initially exposed to in pre-calculus and possibly Algebra 2. And we're going to move into a series of sections in our book where we start learning what a series is, which we were also introduced to in pre-calculus in the form of a geometric series, and start learning how to determine if a series is convergent or divergent. And in today's lesson, we're going to be specifically looking at the geometric series and telescoping series and the nth term test. But we're going to start the journey in today's lesson with an old friend, which is the geometric series and sequence. So here we go. A sequence is just a list of numbers from a function, if you will, or an a sub n, a general term, where the domain, the subscript of your sequence notation, of course, we now remember is the domain of our sequence function, where n is an element of positive integers. So for the course I teach, if we see the double z and a plus sign, that represents positive integers. And we've got our first four terms here. A sub 1 is 10, a sub 2 is 5, a sub 3 is 5 halves, and a sub 4 is 5 fourths. And if we are writing a list of numbers, or indeed a sum of numbers, and we finish with a little dot, dot, dot at the end, that just indicates that the list of numbers or the summation continues for, generally we accept it to be indefinitely. Well, we have a sub 1 is 10. And actually, before I start writing this, recognizing that to get from 10 to 5, we are multiplying by 1/2. And to get from 5 to 5 halves, we're multiplying by 1/2. And repetitively multiplying by 1/2 to make the next consecutive term in our sequence. Then that is a recognition that this is a geometric sequence. And if you come to that realization, the general term of a geometric sequence is equal to a sub 1, or a, depending on the textbook you're using, times r to the n minus 1 power. Now, with that being said, our first term is 10, so we're going to have that a is equal to 10. We see that we are multiplying by 1/2 to find the next term in that sequence, so r is equal to 1/2, and we get a general term of a sub n, which, as a formula, again, a sub 1 times r to the n minus 1 is going to be 10 times 1/2 to the n minus 1 power. So there's a little reminder of the general term of a geometric sequence. Now, if we have a list of numbers and we want to add a finite set of numbers, that means we're going to be doing a partial sum. Again, a content that we've learned in previous courses. So we have 10 plus 5 plus 5 halves plus 5 fourths. S sub 4 would indicate not that I'm getting a list of 4 terms, but S sub 4 is an indication that you want to take a partial sum. And let me add that in there, that this is equal to S sub n. So S sub 4 is equal to 10 plus 5 plus 5 halves, again, plus 5 fourths. And, you know, we can simplify that to equal some kind of number, which I'm not going to bother with in this video because we are in Calc 2. I'm sure we can add some fractions. We have a partial sum formula. Maybe we need the sum of the first 40 numbers, right? We don't want to add out 40 numbers and do all of that addition by hand or even type them into a calculator. The partial sum of a geometric sequence is equal to a sub 1 times 1 minus r to the n power over 1 minus r. So with our example here, if we didn't want to add these first 4 terms, we could say that S sub 4 is equal to the first term, which is 10, times 1 minus r, which is 1/2 to the 4th power, over 1 minus 1/2. 10 times 1 minus 2, 4, 8, 16. So 1 minus 1/16 over 1/2, which is going to be, well, 1/2, or 10 divided by 1/2 is 10 times 2, so that'll be 20 times 15 over 16 after you find a common denominator, of course, with the 1 being 16 over 16. And that reduces, but again, I'm sure you can manage that. Let's move into the idea of series, right? We are in 9.2 and we're learning about series and then starting to learn the idea of determining when they are convergent and divergent. So an infinite sum is going to be a series. That's what a series is. A sequence is just a list of numbers from a function, a sub n, where the domain is positive integers. A partial sum is adding some of finite number of terms in that list of numbers. And an infinite sum, that's what a series is. It's a sum of an infinite number of terms. And even though we're at the end of Calc 2, you'll be surprised by the end of this chapter where we start learning about setting up Taylor and Maclaurin series and polynomials in series, how much we still and how much we need to go back and remember our knowledge, reuse our knowledge, expand our knowledge of the geometric series that we learned in pre-calc. It's just awesome to see how math builds on itself. So that infinite sum formula is S is equal to a sub 1 over 1 minus r if you do want to find that infinite sum, which we can find, which does exist if the absolute value of r is less than, well, between 0 and 1. So if we want the infinite sum of this geometric sequence that I've started this discussion off with, it would be a sub 1, the first term is 10, over 1 minus r, which means we have 10 divided by 1/2, which is ultimately equal to 20. Now, just the fact that we can evaluate the formula, which is S is equal to A over 1 minus R for the geometric series and get an answer of 20 means that, and I just misspoke a little bit, but that does mean that this geometric series of, well, let me write that out, of 10 plus 5 plus 5 halves. Now, if I stop there, that's a partial sum, but if I do a plus dot dot dot, that indicates that my addition is going on forever, and I am doing that sum. I'm adding a list, an infinite list of numbers. But you got to be cautious because S is equal to A over 1 minus R will give you a number, a value, a numerical value, no matter what R is, unless, of course, it's 1, because you can't divide by 0. But if R is 2, you'll still get a number from this formula, but it will not be the actual value of the series. Indeed, the series would be divergent, meaning the sum is equal to infinity or negative infinity. So S sub n, partial sum. Just the letter S, infinite sum. And to summarize that all together, the convergence of a geometric series. A geometric series with ratio of r will diverge. If a series diverges, that means that we understand that the sum of those infinite terms are going to be going to either infinity or negative infinity. And that will be the case if the absolute value of your geometric ratio, the absolute value of r, is greater than or equal to 1. If the absolute value of r is between 0 and 1, then you'll learn when we see the harmonic series that just because the numbers in your sequence are getting smaller, that does actually not guarantee that the series converges. But if the absolute value of r is between 0 and 1, as you multiply by, in this case, like the example of multiplying by a value of 1/2, those numbers are going to get small enough that even though you're adding an infinite number of values, you are going to get a convergence. You are going to get a real sum. And S is equal to the summation, where n starts at 0 and goes to infinity, of a times r to the n power is equal to a, which you may call sometimes a sub 0 or a sub 1 or just some individual or initial value in your sequence, over 1 minus r. So that geometric series will converge, and it will converge to the sum of. Now, I'm not even finished talking about geometric series yet, but we are going to be talking about geometric and telescoping series. These are the only two series that we're going to see in Calc 2 in this chapter that we will not only be able to determine if the series converges, if there is an infinite sum, which is a real finite number, but we'll actually be able to find that infinite sum. For all the other tests that we learn in this chapter, ratio test, limit comparison test, integral test, it goes on and on, we'll be given a series, which means we're looking at a sigma where n starts at some constant and goes to infinity. We'll, for most of the tests in this chapter, only be able to determine if that series approaches a real limit. We won't actually know what that real limit is. We'll get to approximating it much later in the chapter with alternating series and such. But you might note here that here I said the general term of a geometric series is a sub n is equal to a sub 1 times r to the n minus 1. And now I'm writing an a sub n here. A sub n is whatever the expression is that comes after the sigma notation, is a times r to the n. Some of your series in your textbook will be defined with a lower limit of sigma starting at 0, and some of them will be starting with a lower limit of 1. My textbook that I teach out of, not that I wrote, but I teach out of, has a lower limit starting at 0. If, for some reason, you needed that lower limit to be starting at 1, if you have to add 1 to this lower limit, then you would subtract 1 to any location, any n that you see showing up in your a sub n expression. So if I do want to start this off at 1 instead of 0, like my textbook defines, by adding 1 here, I would have to subtract 1 in my a sub n term. And then you could say this is a sub 1 over 1 minus r. Okay. So we are going to determine the convergence or divergence of this, I'm only going to do one example like this, of this series and find S when possible. Okay. We have the summation where n starts at 1 and goes to infinity of a sub n, which is 5 over 2 to the n power. Well, what I can do with this 5 is I can move it out in front of the sigma notation and write this as 5 times the summation, or sigma, 5 times sigma, where n starts at 1 and goes to infinity, of 1 over 2 to the n power. And this is not quite exactly looking like a times r to the n power. I have a power of n, but it's just in the denominator. And you don't know this concept yet, but you might be a little bit confused with maybe a p series, which is different, but visually where all the things are, it kind of looks the same. So remember that, of course, we know that 1 to any power is still going to be equal to 1. So I can write just the numerator of 1 as 1 to the n power, which then takes me to, let's write this over here, 5 times the summation where n starts at 1 and goes to infinity of 1/2 to the n power. Now I can, I almost, to match this notation, maybe we want to see the 5 back behind the sigma notation, but that isn't absolutely necessary. So for this expansion of 5 times sigma, where n starts at 1 and goes to infinity, of 1/2 n to the n power, that expansion would be 5 times 1/2 to the first power plus 1/2 to the second power plus 1/2 to the third power, and so on and so on. And then if I distribute the 5 through here, which now I'm kind of regretting that I took it out, but that's okay to see this, we have 5/2 plus 5/4 plus 5/8, and again, so on and so on. Does this series here, does this series converge or diverge? Well, it's 5a times r to the n's. The given series is a convergent geometric series. We just recognize the pattern. You don't have to write any more than that. Just recognize that it's geometric series with r equaling 1/2. The absolute value of 1/2 is less than 1. Therefore, Well, I already said it, that series is convergent. Now, if it's convergent, let's go ahead and I'll have to erase this, but let's go ahead and find S when possible. What would be the infinite sum? And that's part of the reason I did the expansion, so I could see that first term in the series is 5/2. So our work here is going to be, now that we know that the series, this geometric series does converge, S is going to equal the first term in the series, 5/2, divided by 1 minus 1/2, or 5/2 over 1 over 2, multiply by the reciprocal, and we get a final answer of 5. So this series that we need to recognize as being geometric, and then thus finding that that common ratio is 1/2, is going to converge because we know it's geometric. We know the absolute value of r is greater than 1 and greater than 0 and less than 1, and that infinite sum, it's going to converge to that infinite sum of 5, which kind of looks like an S. So let's write that over again. Okay, let's take a look at our next example. Find all values for x for which the series converges. For those values of x, write the sum of the series as a value of x. Again, sum of the series. If you're told to find the series value, the sum of the series, the infinite sum, you have to understand that you have to be given a geometric or a telescoping series, because those are the only two series that you're going to be able to find the infinite sum if indeed the series does converge. So this really basically must be geometric for this, or potentially telescoping, but right now we're doing geometric, for us to even be able to do this problem. So our base in the numerator and our base in the denominator both have a power of n, so let's go ahead and write that as sigma, where n starts at 1 and goes to infinity, of x minus 3 to the n power, and understand that the absolute value of r needs to be between 0 and 1. So for this geometric, we have an a of 1 and an r of x third. The absolute value of r needs to be less than 1. So we're going to say that the absolute value of x over 3 needs to be less than 1 to meet the condition for this geometric series to converge, which means we have x over 3 has to be less than 1 and greater than negative 1. Now, multiplying all three parts of this compound inequality by 3, we get x has to be greater than negative 3 and less than positive 3. So find all values of x for which the series converges. X has to be between, so this is the answer to our first question, x has to be between negative 3 and 3 for this geometric series to converge. And now it says, for those values of x, write the sum of the series as a function or as a value of x. I almost want to rewrite that as a function of x. So let's see here. Let's get some orange going on. We have a formula for the sum of the series of a geometric series. S is equal to a, or a sub 1, depending on how you're looking at this, a over 1 minus r. So S, we're doing the second part of this question now. S needs to be the first term in the series. We do have a lower limit on our sigma notation of 1. So x over 3 to the first power is going to be a first term of x over 3. And then that is divided by 1 minus your r. What's in that parentheses? X minus 3. So let's find a common denominator. And we have this is equal to x over 3 divided by 3 minus 3, 3 minus x, over 3. When your numerator and denominator have the exact same denominator, so when you basically multiply instead of dividing by that fraction, when you multiply by the reciprocal, those common denominators of 3 are going to cancel out, and our final answer is that S, let's keep this in black so it's easier to read, S is equal to what? X over 3 minus X. And just to make sure I didn't say something silly, boom, there is our final answer and our introduction to determining the convergence or divergence, even though both of our examples here were convergent, of a geometric series, and then if it does converge, what is that infinite sum? Let's move on to the last 2 tests of this lesson. So let's do an example of telescoping series, which I had to relearn calculus like after 20 plus years of being in college to teach it in my high school. And that was really tough because my memory was not good enough to recall information from 20 plus years ago in a class that I took one time. So this sentence I found to be very, very confusing. And it's not necessarily in the section of notes in your textbook where it starts talking about what a telescoping series is. It just says if the partial sum converges, then the series is said to converge, and it converges to S. Okay, I don't understand. Well, I do now, and hopefully I'm going to help you understand. Okay, first of all, of course, if you see the phrase partial sum, that's S sub n, okay? So you have to be able to come up with a expression, a formula that gives you the partial sum of some series. Then the series, okay, so the series is an infinite sum. So when you see the word series, you're thinking, okay, it's not a sum of a finite number of terms, it's a sum of an infinite number of terms. That sum is said to converge. If a series converges, then the infinite sum approaches some real finite value, some real limit. If a series again diverges, then its infinite sum is going to either infinity or negative infinity. And it converges to S, okay? That means that we're not only going to determine if a series converges, but we are going to be able to find what that infinite sum is actually approaching. That only time you can do that in at least chapter 9 of your Calc BC book, or at least it is out of the one I'm teaching out of, when you're first learning how to determine the convergence of and divergence of series, is the geometric and telescoping series. So right away, I know it's got to be just by this statement, you're going to find the S that your series converges to. You're going to be able to find that infinite sum. It's got to be either telescoping or geometric. Okay, so if the partial sum converges, which means that we have some kind of S sub n expression or formula, and we are taking the limit as n approaches infinity, because that's what you're doing. You're analyzing limits to determine convergence or divergence, and that is giving some kind of real limit. Now, if the limit as n approaches infinity of S sub n is equal to a limit, well then what? Then the series is also said to converge, and it converges to S. So S is going to be that real limit that you get when you analyze the limit as n approaches infinity of your partial sum formula. But you need to be able to come up with a partial sum formula. So S sub n is going to be some kind of a sub 1 plus a sub 2 plus a sub 3 and so on and so on. But I don't want this to go on forever like it's a series. I'm trying to write a formula for a partial sum, so I'm going to do one last plus sign and do an a sub n. So you're going to need to be able to look at the question you're given and come up with a general term that creates the values in that list of numbers. And then you're going to be looking for a lot of cancellation to occur to be able to simplify this possibly long expansion of a finite number of terms and see a simplified partial sum formula that you can then, analyze the limit of. So here is our example. And by the way, I haven't forgotten, we really are going to be learning 3 different types of convergence tests in this chapter. We have the geometric series, the telescoping series, but there is an nth term test that should always be done before you do any kind of significant amount of work to determine if a series converges or diverges, and that is going to be the nth term test. I'm saving that for last though. So we have determine if, we have a sigma notation here, sigma where n starts at 1 and goes to infinity, so a series notation basically of 1 over n squared plus n. Determine if that converges or diverges, and if it's convergent, find s. The only time you're going to be asked to find the infinite sum is if you are looking at a geometric or telescoping series. And this does not look like a times a common ratio to an n power, so this is not going to be geometric. And you also, besides the fact that you're being asked to find the infinite sum, and you know it's not geometric, you have a telescoping series. There's a good chance that you're going to be working through the process I'm doing right now if you realize that the denominator of a sub n is factorable. So what do we have? We have sigma starting at n equals 1 going to infinity of our 2 terms in the denominator both have a common factor of n. So that's going to be n times 1 plus n. Now, we need to recall, to finish this problem and come up with an s sub n equation, we need to recall our partial fractions. And again, we only need to worry about the simplest setting of partial fractions, which is where we have a constant in the numerator and a quadratic in the denominator that yields 2 unique linear factors. There are more complex settings for partial fractions, and if you want, I'll put a link in that description below. So we need to break out some partial fractions. So 1 over n times 1 plus n is going to be equal to some kind of constant over n plus some kind of constant over 1 plus n, or n plus 1. Okay, so I'm going to take this equation and multiply both sides by n times 1 plus n. And when I do that distribution, I'm going to get 1 is equal to a. Now the factors of n will cancel, so we have a times, and I'm bothered by the ones first, so I'm going to do n plus 1, and then plus as we go to our second term on the right-hand side, the n plus 1 factor will cancel out, or 1 plus n, and we'll have bn times n. This is an identity that's supposed to hold true regardless of what your values of n are. So I'm going to pick the easiest values that I can possibly come up with, and shortcut what potentially could be, for a lot of partial fraction problems, a pretty complex situation. We're going to let n equal 0. And when we do that, we're going to have 1 is equal to a times 0 plus 1, which is 1. So basically, a is equal to 1. And I'm picking n of 0 for the sole purpose of removing the variable of b in this identity, leaving us with just the variable of a. Now, for the next super convenient value of n that I want to pick, I'm going to pick an n value of negative 1, so we get the variable of a to cancel out for our second line of work. So we have, if we let n equal negative 1, we're going to have 1 is equal to, I think this time I'm going to show it, a times negative 1 plus 1 plus b times negative 1, which is going to yield us 1 is equal to negative b, meaning that b is equal to negative 1. So I can rewrite now this sigma notation, this series, to be equal to sigma starting where n is equal to 1 going to infinity of, okay, let's see here now. A is 1, so we're going to have a 1 over n. And this is a plus b, and maybe let's do this right now. Let's take this b and move it out in front of the fraction and have b times 1 over n plus 1, or 1 plus n. And b is negative 1, and so we have minus 1 over n plus 1. For a telescoping series, once you factor that denominator and go through your partial fractions process, expect to see two terms being subtracted together. Now we're going to use that difference of two terms to start expanding out in S sub n, a partial sum formula. So we have S sub n. Okay, now let's let n be 1 and start this expansion. So with looking for a sub 1, we're actually going to get two terms, but we have 1 over 1 minus 1 over 2. And now we're going to look for, or let n equal 2, and get 1 over 2 minus 1 over 3. And then plus letting n be 3. We're going to have 1/3 minus 1/4, right? Because 3 plus 1 is 4. Now, if you look at the beginning of this expansion, you're going to start seeing that all these constants are starting to cancel out. We have a positive 1/2 and a negative 1/2, and a positive 1/3 and a negative 1/3. And I'll give you a hint. The symmetry of the way these terms cancel is going to be the same on the initial a sub 1, 2s, and 3s, and then coming in from the right-hand side with the a sub n's, a sub n minus 1, and so on. But I do want to show, I just think it's good for teaching to show the expansion of our partial sum from both directions to get, as deep of an understanding I can for my students. And the bigger the gap is between these denominators, like if this were n and n plus 3, you would have to continue this expansion quite a bit more before you start seeing some terms cancel and you have a more complex S sub n expression. But coming in here at a sub n, or our general term, our a sub n is going to be, well, this is our a sub n term, our general term. So we have 1 over n minus 1 over n plus 1. A sub n minus 1 is going to be, we're having to take n out and replace it with n minus 1. So we have 1 over n minus 1 minus, now if we put n minus 1 in for n, we're going to have n minus 1 plus 1, or 1 over n. Now the cancellation is already starting to happen, but I'm going to do one more expansion here just to make sure that you follow what I'm doing. So a sub n minus 2. N minus 2 is going to go in the location of every n. So we have 1 over n minus 2 plus, minus 1 over n minus 2 plus 1 is going to be n minus 1. And then there's an undetermined amount of terms in between, starting from the left and coming in from the right. But what do we have? We have a 1 over n and a negative 1 over n. So those are going to cancel. We have a positive 1 over n minus 1 and a negative 1 over n minus 1. So indeed, everything is going to cancel in our S sub n expression. Isn't this cool? We're just going to get a nice little S sub n is equal to 1. And then what's left on the right-hand side? 1 minus 1 over n plus 1. And now, I don't know why I'm putting a parentheses there. Now we have an S sub n expression, like this sentence is kind of indicating that we have. If the partial sum converges, well, now we have a partial sum formula. If it converges, meaning we're going to take the limit as n approaches infinity of that expression. So the limit as n approaches infinity of 1 minus 1 over n plus 1 is equal to, and this isn't the world's most exciting problem because we're going to get a nice, very almost anticlimactic value of s, but this is going to be equal to 1 minus 1 over, as n approaches infinity, you're going to have 1 over infinity, which means that's going to approach 0, and we get an answer of 1. So the limit as n approaches infinity of what? Of S sub n is equal to 1. And therefore, because this is a real finite limit, therefore, the given telescoping series converges because our partial sum converges, and it converges to an S value of 1. Okay, so that is an introduction anyway to a telescoping series and how to analyze whether, how do you recognize that you might have a telescoping series? The denominator is factorable. You go through the partial fractions, you get what's more than likely going to be a difference of terms. You do an expansion to create an S sub n equation. Analyze that where n goes to infinity. The limit as n goes to infinity, if you get a real limit, that given series converges basically by the fact you recognize that it's a telescoping series, or maybe you could say the telescoping series test. Okay, whew, we are almost done. Before you do any work of thinking about whether a geometric series converges or diverges, if what potentially is a telescoping series converges or diverges, or indeed any series you're given in this chapter that we have a long road to go down through still, you should be thinking about the nth term test. So the limit of the nth term, the general term, of a convergent series, if a series of a sub n converges, or basically just if you have a series that you know converges, then the limit as n approaches infinity of a sub n, it is 0. But the converse is not true. If the limit as n approaches infinity of a sub n is 0, that does not mean that your given series converges. If it did, this chapter would be a whole lot less work. We would only need the nth term test, but we've already learned just in this first section about determining, learning what a series is, or being reminded of what a series is, and determining if it converges or diverges. We've already learned about two types of series that we need to be aware of. But if the limit as n approaches infinity of a sub n, your general term, does not equal 0, then you are guaranteed that your given series diverges. So here we have a few examples of just, does this series diverge? We have sigma, where n starts at 1 and goes to infinity, of 4 to the n over 3 to the n. Well, this is equivalent to sigma, where n starts at 1 and goes to infinity, of 4/3 to the n power. This is a geometric series with the absolute value of r, which is 4/3, is not, or actually is, greater than 1. So this is geometric with the absolute value of 4/3 being greater than 1. Therefore, this series diverges. Our second example, or this example right below it, is we have sigma starting at n, where n starts at 1 and goes to infinity, of 5n squared minus 1 over 6n squared minus n. Well, here our a sub n is just a nice simple rational function, if you will, or expression, where the numerator and denominator are both polynomials. The limit as n approaches infinity of 5 to the n squared minus 1 over 6 to the n squared minus n. When the numerator and denominator of a rational function or expression have the same degree, then your limit is going to be equal to the leading coefficient of the numerator and denominator. So this limit is equal to 5, 6. This is not equal to 0. Therefore, this given series diverges by the nth term test. And you do want to name the test that you're using to justify whether a given series converges or diverges. Here we have a series where n starts at 1, we have sigma where n starts at 1 and goes to infinity of 3 times e to the negative n. Well, that is equal to sigma where n starts at 1 and goes to infinity. You might just say the word series. By the way, if you're talking about series and you just see sigma, that's just kind of like shorthand notation for the fact that it's a series. The convergence or divergence of a series is not dependent on where n starts. If convergence kind of doesn't, if you don't pass a convergence test until n is 10, it doesn't make any difference. So again, if you see just sigma when you're talking about series, that's series notation. It's kind of implied that the upper limit is infinity. Well, e to a negative exponent is 3 times, it's equivalent to 1 over e to the power of n. And see, now I've written this as a times r to the n power. This is a geometric series with r being equal to 1 over e, the absolute value of which is less than 1. Therefore, we can say more specifically, does this series, does it just diverge? We can actually say, no, it doesn't diverge. It actually converges. And ultimately, we could find that infinite sum if we would like to. But this series, this our third example, does converge, even though I just wrote the question as, does the series diverge? Mainly for this question right here. We have sigma starting where n starts at 1 and goes to infinity of 1 over n. Now, we're going to be talking about whether or not this is a famous series. This is actually called the harmonic series. It's kind of interesting. When you expand out n, when you let n equal 1, you have 1. When you let n equal 2, you have 1/2. And when you let n equal 3, you get 1/3, and so on and so on. And this addition goes on forever, and the terms that you're adding by are getting smaller and approaching 0. But crazy, it's a little bit crazy that these numbers, these terms in this series actually do not approach 0 fast enough. This famous harmonic series, well, if you do the nth term test, the limit as n approaches infinity of 1 over n is actually equal to 0. This harmonic series diverges, and we're going to prove that using the integral test in the upcoming section. But for right now, does this series diverge? Well, the limit as n approaches infinity of a sub n is equal to 0. Remember, the converse of this statement is not true. Just because the limit as n approaches infinity of a sub n is 0 does not mean that the given series converges. It just means you don't know the answer. This series, though, is not guaranteed to diverge because this limit is not equal to 0. And that is my last example. I'm Mr. True. Bam! Go do your homework.